All right, so this is a double slit problem, but it's not with light, it's with sound. So what we have are two speakers, and they tell us in the problem that the sound wave, right here, the sound waves from the speakers are in phase. So what that means, like if you looked at the sound waves are not transverse, but let's just show them as being transverse, you know, like this. So the sound wave from this speaker would be like that, and then like that. So see, they're in phase with each other. Okay? So, you know, if we looked at point P right here, how would these sound waves come to point P? Would they be together or not together? Together, right? They're supposed to be together here. They're like in phase. So what would we get at point P? Loud or quiet? Loud. Point P is going to be a loud spot. Now, if you go to a point that's, you know, up here, is it possible for the sound waves coming from the speakers to hit that point out of phase? You know, like one wave is at a peak and then the other wave is at a trough. Yeah, what would you get there? You'd get a quiet. Now, look, the loud would be referred to as a maximum, max. The quiet would be referred to as a minimum. That's what they're saying here in the problem. They're like, here, minimum. Where else over here? They talk about maximums and minimums. Okay, so the pattern's going to go like this. The pattern's going to go like this. So we're going to have maximum, minimum, maximum, minimum. That's the pattern, right? When we did this with light, it was bright, dark, bright, dark, bright, dark, but same thing, maximum, minimum. So here we'd have minimum, maximum, something like that. You know, the pattern continues. Okay, first question. Let's start calculating. A, calculate the wavelength of these sound waves. Super easy. What's the equation for the velocity of a wave? Wavelength times frequency. So the wavelength is going to be velocity over frequency. They give us the velocity right here. They give us the frequency right there. Right, so we're going to go 343 meters per second divided by 2,500 hertz. And then this gives us the wavelength, which is 0.1372 meters. You could just round that to 0.14. That's fine. Okay, so that's the wavelength of these sound waves. Okay, part B. The student moves a distance y to point Q and notices that the sound intensity has decreased to a minimum. So you know what, my little pattern that I wrote out here? Too tight. Got to spread this out. So we got a maximum there. So what they're telling us is that at point Q, we have a minimum. It's quiet. What do they want us to find? Calculate the shortest distance that the student could have moved to hear this minimum. Now, the equation, and I'm not going to go over the derivation of this. You can watch the lecture. I did a lecture on this that's posted. The equation that applies here is y equals lambda L over D. And dudes, you don't have to memorize that equation. It's on the equation sheet the College Board gives you. It's right there on the equation sheet. And then it's either going to be m like that or m plus 1/2. Which one do we want for this situation? Do we want m or do we want m plus 1/2? Which one corresponds to the minimums? The minimums are where the waves cancel each other. You want the 1/2. If you're like, what the heck? Watch my lecture. I explain it in the lecture. This is all about waves either adding to themselves, constructive interference, or subtracting from themselves, destructive interference. So if you're dealing with a minimum, this is the equation. Okay. So the variables. What's D? D is this. It's the distance between. You know, if this were light, and in my lecture I said it's the distance between the slits, but here it's speakers. So D is going to be the distance between the speakers. L is the distance from the speakers over to where we're observing this pattern. That's L. We calculated lambda. Now, what's this M here? M is referred to as the fringe order, you know, and it's how we keep track of the pattern. You know, so you get this pattern of, like, you know, when we were doing light, so like it's like this. When we were doing light, it was like bright, dark, bright, dark, bright, dark, and then the pattern goes dark, bright, dark, like that. So look, the center guy is what? M equals what? 0. This guy is M equals 0 for dark. This guy's M equals 0 for dark. Then it goes M equals 1, and this is and this is M equals 1. And then this would be M equals 1, M equals 1, right? So this is 0th order bright, 0th order dark, 1st order bright, 1st order dark, right? It goes like that. So what they want us to do is figure out the first possible minimum. So what's this going to be? This is going to be M equals, so kind of look at this pattern I did right here. This is going to be M equals what? For the first minimum, 0. This is M equals 0. So we set that equal to 0, and what we have is Y equals lambda L 1/2 over D. And then they're asking us to solve for Y, so we just plug straight into this. Okay, so what was our lambda? Our lambda was 0.14. Actually, don't use the rounded though. Don't use rounded numbers here. 1, 3, 7, 2. L is this, 5 meters, and then the 1/2. And then D is the distance between the speakers, 0.75. Bam! This gives us the answer, which is, I'll just round this off to 0.46 meters. Right? So if you come down from this point here, if you come down 0.46 meters, that's where the first quiet is going to be. The waves cancel. We get a minimum there. Okay, C. Identify another location on the line that passes through point P and Q. What would be the easiest point to identify? Any point on this line right here. Any point. I'll give you a hint. The pattern going up is the same as the pattern going down. So what would be the easiest acceptable answer? So we just calculated this Y is 0.46 down. So what if we went like this? What if we went up 0.46? Should that be a quiet up there? Yeah. That's total. In fact, that's the answer that they have on the answer key. Or if you wanted to do the hard way, you could figure out the next minimum. If you continue down farther, you could figure out the next minimum. But what you'd have to do is you'd have to go back to this equation and plug in M equals what? Change this, instead of being 0, which is what we did, make this M equals 1, right? And then this parentheses would give you 1.5. Okay? All right, we're almost done. D. How would your answer to part B change if the two speakers were moved closer together? Oh my gosh, it doesn't get easier than this. All you got to do is look at this equation. Look at this equation right here. So what variable are they messing with in this equation? D. If D got closer together, well, what are they talking about? Making D bigger or D smaller? Smaller. If D gets smaller, what's going to happen to Y? It's going to get bigger. That's the answer. Y gets bigger. That's what they're looking for. The spacing will become, the spacing between the loud and the quiet gets larger. Okay, last question. How would your answer to B have changed if the frequency was increased? Ooh, if the frequency increased. All right, so look at our equation here. Look at this equation. Is frequency in here? No. But you should realize that frequency is related to something. See, look, in the velocity equation, velocity is wavelength times frequency. Velocity for a given wave remains what? constant. I mean, the speed of sound is the speed of sound, whether it's a high frequency or a low frequency. The velocity of the sound is going to stay constant. So if the frequency, what do they say? Hold on. If the frequency increased. So look, increasing the frequency is going to do what to the wavelength? Decrease it. An increase in frequency is going to decrease the wavelength. If wavelength decreases, if that goes down, what's going to happen to Y? It's going to go down. And that's the answer. Y will decrease. The separation between loud and quiet will get closer.